All right, welcome to Friday, October the 2nd. It's hard to believe it's already October. AP Chemistry. So we've been, after the quiz, we've been just reviewing a little bit of what we've been talking about, okay? And I do want to, and move this over here, please. Just keep talking a little bit about vapor pressure, because boiling occurs when the vapor pressure of the liquid equals atmospheric pressure. So in other words, in that bubble when water is boiling, the molecules have to be pushing out more than the atmosphere is pushing down, because the atmosphere is pushing down saying no, the bubble can't form. Because if the bubble forms, the liquid raises up some. But the atmosphere is pushing down and saying no, it can't happen. So what we do normally is we put the pot on the stove and we begin heating it up. Well, if molecules move faster, they're obviously going to evaporate quickly, they're going to be moving faster, and they're going to have a greater pressure. Until finally the pressure equals atmospheric pressure, which we know to be 760 millimeters of mercury. Okay? When that happens, we call that the boiling point. For water, that's 100 degrees. Now, if something has a smaller, it's a weaker attractive force, it's got to have a lower vapor pressure, well then as we heat that up, pardon me, I'd say that backwards. If something has weak attractive force that has a higher vapor pressure, as you heat it up, it's going to reach this 760 sooner. So its boiling point will be way down here, it'll make way less. Okay? So the vapor pressure equals atmospheric pressure is when boiling occurs. So the reality is the boiling point of water changes every day. Because as this pressure changes, if the pressure is dropped down to here, like a low pressure system where you go up into the mountains, now water's going to boil here. If a high pressure system came through and we're up here, well, water may boil just a little bit hotter than 100 degrees. Now, we're talking like fractions of a degree, based upon small pressure changes that weather brings. But if you have a pressure cooker, have any of y'all ever heard of a pressure cooker? Yeah. Okay, the lid seals on it, the steam can't come up. Well, that takes the pressure way up here, which means the water is somewhere between 140 and 160 degrees Fahrenheit. No, it's going to be Celsius, pardon me, because it boils at 100. Okay, so it's going to be somewhere much hotter, so your food's going to cook quicker. Okay? Did I hear somebody just knock at the door? No? All right. So, does everybody understand the relationship between vapor pressure, boiling, attractive forces? That's huge.
Yes.
Okay. And the other thing on that, and make sure on that practice problem that we did, they showed you formaldehyde, okay? And they said, where is a hydrogen bond going to form? Okay? Now, normally I wouldn't say a hydrogen bond is going to form here because there's no hydrogen attached to this, but this still is going to be your negative end. So how's water going to come in and do that?
Hydrogen bond to the box.
So it's going to be here, right? I think that's what you're mumbling. Now, what I really want to point out about that particular question is the wording. Because it says, show where a hydrogen bond is formed. So if you use the what is that A? What's the grammar? Is that a preposition? It's not a preposition. No. Article or something. The A means one, right? Then it specifically said use a dashed line to represent the hydrogen bond. So make sure that you read the question carefully. So this is my hydrogen bond right here. This is not the hydrogen bond here. Somebody in first period asked, well, can the oxygen come here? Could this be a hydrogen bond? And the answer is no. Why not?
Because that hydrogen isn't bonded to an oxygen.
So what does that mean about the polarity or the positivity of this hydrogen?
It's
not very positive. The carbon and hydrogen have nearly the same electronegativities, so it's a relatively even sharing of electrons. So it's not a very positive charge, so there's no real attraction there. Whereas here, with this oxygen, the electrons are being drawn strongly this way, exposing that nucleus, making it a very distinct positive charge. Okay? And this is a very distinct negative charge, and so the two can combine together there. You don't have the positive charges here. It's only when the hydrogen is attached directly to the fluorine, oxygen, or nitrogen. And for fluorine, your only molecule is HF. That's the only one you're going to have with fluorine in it that's really going to form hydrogen bonds. Because the hydrogen has to be attached to the fluorine, oxygen, or nitrogen. Fluorine can only form one bond. So the only thing fluorine can be, you know, if it's going to have hydrogen bonds, the only thing it can be is HF. So we really need to look for anything with an OH or a NH in it. That's going to be our clue. That's going to be hydrogen bonds. So we talked about fat versus water-soluble vitamins. What was the difference? In that article, which I know you all read, so why is this one not soluble in water and this one is? Okay, but you can't just say like because it's polar. In terms of attractive forces, this is mainly non-polar, right? So what's going to be the attractive force with it in water? Not lattice, that's ionic compounds only. Dipole-induced dipole. There's one place over here that we can form a hydrogen bond with water, but the rest of this is only going to have the very weak induced dipole-dipole attractions. Okay? Whereas look at all the OHs here, all the different places hydrogen bonds can form here on the vitamin C. As a result, there's much stronger solute to solvent attractions, causing it to come into solution here. Here, there's very weak solute to solvent attractions, not great enough to overcome the much stronger hydrogen bonds holding the water molecules together. So water does not separate, and as a result, it doesn't dissolve. This is another question. They'll give you two molecules, or even just sometimes one, and say, explain why it is soluble or it is not soluble in water. And you have to then identify, okay, does it have hydrogen bonds in it? Is it nonpolar? Then you have to state the type of attractive forces between the solute and the solvent. Are they strong enough to overcome the solute-solute or the solvent-solvent attractions, or are they not? If it's soluble, it is. If it's insoluble, it's not. Okay? So that's just a practical application here. And then I just talked about if you take mega doses of vitamin C, like some people proclaim you should, like if you're fighting a cold or a flu, since it's water soluble, that just means you're probably going to pee out most of it. You know, it's just going to dissolve, you know, and just go. Whereas this is going to collect in the fat and be much more long term. So this lead kind you have to be careful of overdosing on because they're going to stay around for a while because they stay in the fat. All right, so that's just some practicality. Now, where we ended up. And the reason why I keep just kind of going over this is just these are solutions and the IMFs. I would say probably 15 to 20% of the AP test. There's a lot of questions about this stuff on there. So it's real important. That's why I just wanted to keep harping, making sure you understand the little nuances. All right. So in terms of energy, we talked about solute plus solvent yields a solution. Okay? So we have our delta H1, our delta H2, and our delta H3. Okay? Our overall heat of solution is going to equal to delta H1, which is solute to solute, plus delta H2, solvent to solvent, plus delta H3, which is solute to solvent. Okay, so all these are your three, but they're all occurring at the same time. Okay, what do we know about the sign of these two? They're both positive. Okay, and this one is negative. So what's going to determine the overall sign of the delta H of solution? So in terms of math, what's going to determine this? If 1 plus 2 is greater than 3, what's the sign going to be? Positive. If 1 plus 2 is less than 3, it's going to be negative. Okay? So now, most of the time we're going to be talking about ionic compounds. So this is what we're going to refer to as the lattice energy. This is your energy of hydration. What do you think that is? When the water molecule attaches. So the lattice energy is how much energy does it take to pull the ions apart. Okay? The energy of hydration is the energy released when the water bonds to the ion. Bonds forming always release energy, bonds breaking always requires energy. So when it comes in, that's going to be your energy of hydration, how much energy is released when that bond forms. Okay? So the question is there enough? Now remember, more than one water molecule comes in and surrounds. And so you get, each time a water molecule hits it, you get more energy released because there's more bonds forming. Okay? So it's all going to kind of look like this and then pull it into solution. So if we have a positive heat of solution, what does that mean about the lattice energy compared to the energy of hydration? It's greater. So the lattice energy is greater. Come on, Steve, you can do it. Is greater than the energy of hydration. But if we have a negative delta H of solution, what does that mean? It's less than. Okay? So we can just know by just the sign. Now most of the time, the value of delta H is pretty close to 0. It's not very far away. The farther away, the more the temperature change is going to be. Okay? So when you dissolve sugar into water, you don't notice much temperature change. You put salt into water, you don't notice much temperature change. But in an ice pack, you have one of those disposable ice packs, you mix them together, it gets super cold. That's going to mean the delta H is going to be very positive. It's going to be a big number. When something gets really hot, when I put sulfuric acid, concentrated sulfuric acid into water, it gets the hot to where the water will almost boil. Okay? It's going to have a very negative, very big number, but negative heat of solution. Okay? So, what's going to happen then if I have a positive heat of solution? What's going to happen to the temperature of the solution? It's going to get hot or cold?
Cold.
The surroundings get cold.
Okay? The surroundings get cold, and that's what we observe. So the beaker, the test tube, the whatever is going to get cold. Okay? So at the very end, hopefully you guys stuck with it. How can something that's absorbing energy get cold?
It's taking energy from the surroundings, so it's getting cold around it.
Okay? So somebody else tell me what she just said.
It's taking in the heat from the things it's touching.
Okay? So you have the system and you have the surroundings. okay? In the system is the actual things that the solute and the solvent, the actual molecules that are being broken apart and then the water attaching to. But you have a whole bunch of other water molecules that aren't touching anything. You have the beaker, you have the air around it, you have your hand, all of those things that aren't actually reacting. So, bonds breaking, bonds forming always involves potential energy. If I go and take this rubber band, I do work and I put it into this. I did not change the temperature at all. Temperature is a measure of how fast the molecules are moving. Potential energy is energy of position. What are the things bonded to? Okay? So as I stretch this, I've done work, I put energy into it, it's absorbed it as potential energy. It now has the ability to release that energy back, and that's why it hurts when it snaps and hits you, because it's releasing that energy. Okay, so the same amount of force that I put in to stretch it is going to be released when it comes back together. Okay? But that's all potential energy. A thermometer does not measure potential energy, it only measures kinetic energy. So the surroundings, your beaker of water, okay, you're doing the reaction in it. Well, the surroundings, the energy is going in, the kinetic energy is leaving the surroundings and going into the system to break the bonds and to form the bonds, okay? So, the law of conservation of energy says energy is neither created nor destroyed, it just changes form. So as energy goes into the system, endothermic, it's got to come from somewhere. Well, it comes from the surroundings, so the surroundings go down. They get colder. So we observe the surroundings, but we're measuring the system. That's why they're opposite. On the other hand, if a system is giving off heat, exothermic, that means the products have less energy than the reactants. They release that energy. Well, where's that energy going to go? To the surroundings. So the surroundings go up, they get hot. So we observe the surroundings, we're measuring the system. Together, the total energy stays the same. That's huge, that's a big concept too. All right, so practical application of all that. How does temperature affect the solubility? Well, what do we know, generally speaking? Well, right, you do your dishes in hot water because the grease dissolves better in hot water than it does cold. If you have really dirty clothes, you want to wash them in hot water, not in cold water. Okay, you want to wash your hands with more for comfort, but it also helps. Hot water helps get things off better than cold water does. Okay, you can dissolve more sugar and make your sweet tea in hot water, put a whole bunch of sugar in it, and then let it cool down. Okay, so if we have a positive delta H, not struggling here, positive delta H of solution, okay, that means that it's endothermic. So where would heat go in my equation here? Where would heat go? On the left or the right? Are you adding heat or is heat being released in an endothermic reaction? Adding heat is positive. So I'm going to say heat plus solute plus solvent goes to a solution. And I'm going to write a double arrow, meaning that it could come back the other way. We know that we can precipitate out. We just did that with our green crystals. If you lower the temperature, you change the temperature, you can precipitate out. So it's a reversible reaction. Now, in order for equilibrium to occur, you have to have what's called a saturated solution. What do you think a saturated solution is? Can't dissolve anymore, it's full. So you have some sugar sitting at the bottom, you have some salt sitting at the bottom, okay? So when you have that, and you have some sugar down here. Some of the sugar is up in here as well. These circles are sugar molecules, and they're going to be surrounded by water. But there's just so many that can fit. Once you can't get any more, it's saturated, it's full. But every once in a while, this is called a dynamic equilibrium. It is not static. In other words, it's changing all the time. So some sugar will then dissolve. But there's only so much room at the end, and that forces another one to precipitate back out. So it's a reversible. So the definition of equilibrium is the forward rate is equal to the reverse rate. So the rate of dissolving is equal to the rate of crystallization. You follow me on that? The only time that's going to happen is if you have some solid sitting on the bottom. If there's no solid at the bottom, then nothing else is dissolving. Okay? But we have a saturated solution. Okay? Hey, Advite, I want you to do me a favor. I want you to go into the lab prep room. Just fill this there's an ice machine in there. I want you to go just fill this cup up with ice and bring it back to me. It's going to be the second door on the right. So, there's a thing called LeChatelier's principle. You guys you're gonna have to just write this definition down. I'm not gonna write it. LeChatelier's principle. When a stress is applied, you guys are still writing LeChatelier. Does anybody take French in here?
Oh, I took AP French last year.
You did? How would you pronounce that in French?
Good question.
Taking it does not mean we know.
LeChatelier.
That's the way I pronounce it, but I've heard scientists, on videos and stuff
Probably
say it all kinds of
But
different
are they
ways.
French science?
Well, I don't know. That's what I'm saying. So they might be botching it as well. So I say LeChatelier. I say it like it's English, LeChatelier.
Yeah, and just add a little bit of Frenchness to it.
Abbreviate it. LeChat.
So you got to talk in a more feminine voice. Is that what you're saying? Is that how you have more Frenchness to it?
Yeah. I got the highest score in my class on the AP exam.
Oh, that's good.
Yeah, it was a 2.
I always say there's no way a French guy can sound masculine and there's no way a German woman can sound feminine, just because of the way the language is.
Yeah.
So, perfect, thank you.
Go that way.
Okay, so we have a saturated solution, it's maximum amount. Now, I probably shouldn't have said that on video. People in France are gonna start making comments on my YouTube channel. The heat, so I'm at equilibrium, that means I'm balanced. Okay? But now all of a sudden, I add some heat to this, I put some fire to it. Now all of a sudden I'm adding heat to this side. Well, LeChatelier's principle, we ready to write the definition? Okay? When a stress is applied to a system at equilibrium, when a stress is applied to a system at equilibrium. Do I have it written right there in the notes? Anastasia, is it there? Yeah. When a stress is applied to a system at equilibrium, comma, the system will shift in such a way as to relieve the stress. The system will shift in such a way as to relieve the stress. How am I word for word there on that? Pretty close?
I think it's like word for word.
So I've only said it a few times. Okay, the system will shift in such a way as to relieve the stress. Okay, so what does that mean? Okay, so I'm balanced. I think of a teeter-totter on a playground. Okay, I'm balanced. And then all of a sudden, some heat, I put it onto a fire, or I set it out in the sun. I'm adding heat to it. I throw it out of whack. I'm no longer going to be at equilibrium. Because if I add heat here, all of a sudden now these molecules are going to be going faster. They're going to dissolve more. So the forward rate is going to be greater than the reverse rate. Okay? So the reaction is here. In order to get to equilibrium, I added heat. I have to use up that heat, so it's going to shift this way to rebalance. Okay? Just like on a teeter-totter, if somebody jumps on this side, you got to put more weight over on this side to balance it out. Right? And so as a result, if you add heat here, it's going to shift to relieve the stress. In other words, it wants to use up that heat that you just put in. So it's going to push it this way, and more is going to dissolve. This means it's together, it's dissolved, it's here. Solute plus solvent, two separate terms, means it's the solute is separated from the solvent. It's sitting at the bottom. Okay? So this side, it's sitting at the bottom. This side is dissolved. Adding heat pushes it to being dissolved in an endothermic reaction. So we know that most of the time, an increase in temperature is going to mean an increase in solubility, which means that most substances have a positive heat of solution. Okay? Depending upon the value, the farther away it is from zero, the more effect temperature has. The closer to salt, salt's heat of solution is like 2. It's real close to 0. So when you increase the temperature of salt, salt is about the same solubility in hot water as it is in cold water. It doesn't change hardly at all. But our green crystals, very soluble in hot water, very insoluble in cold water. It's going to have a much greater positive value for your heat of solution. Okay? So the reverse of that, a negative delta H of solution, is exothermic. Okay? So now it's going to be solute plus solvent. But this time heat's going to be generated like a product. So we're going to get solution plus heat. So now heat's on the other side of the teeter-totter. Or the seesaw. What do you guys call them? Seesaw, teeter-totter? Seesaw. I see you, I saw you, I see you, I saw you. So a seesaw. Now heat's over here. So what's going to happen when by adding more heat? Which way is it going to make the reaction go? Backwards, the other way, towards, in other words, it's actually going to decrease the solubility. Now that seems backwards, but this is true for all gases dissolved in water. In lakes and streams and ponds, there's more oxygen dissolved in the wintertime than there is in the summertime. You're more likely to have a fish kill in the summer than you are in the winter because of lack of oxygen. Okay? And so as a result, you add heat, the solubility decreases. This is true of all gases. It's the opposite of solids and liquids in water. Because you know, if you leave a soda out in the sun, it's going to go flat really fast. That's the CO2 dissolved in water. Okay? So, temperature, if you have a positive heat of solution, it causes an increase in solubility, which is most. If you have a negative heat of solution, it's going to cause a decrease, which is rare for solids and liquids in a liquid, but it's true for all gases in a liquid. So an increase in the temperature of a gas in a solution is going to always decrease the solubility. It's going to force, you'll see bubbles, you'll see it coming out of solution. Okay? Now, before I move on to gases, what would an unsaturated solution be? Let's clarify it a little bit. Not dissolved. What?
Like haven't reached exactly.
Right. There's still room. You haven't maxed it out yet. Okay. That can mean you have 1 grain dissolved up to 1 grain short of saturated. So unsaturated, you know, is just the diluted version. Okay. There's more. You can put more in. What's a supersaturated solution? When it's over. So can I just add more stuff in here to make it supersaturated? No, you have to make a saturated solution at a high temperature and then cool it down slowly. Now, only a few substances form supersaturated solutions. Sugar is one of them, okay? And for some reason, as it's cooling, the solubility should be decreasing and it should precipitate out like our green crystals did. But every once in a while, they form a supersaturated, this unstable condition to where nothing precipitates out. I always like it as peer pressure amongst the ions, that nobody wants to be the first one to leave the party. Nobody wants to be the first one to precipitate out, okay? In Baton Rouge, when I taught at Baton Rouge High, they had the prom at a hotel every year, Belmont Hotel. And the kids would always tell their parents, we need to get a couple of rooms just so we can change clothes after the dance, go to the after party. Well, it turns out the after party was at the hotel, okay? And so they always had these rooms. Now, the rooms are designed for 4 people, but they put 15, 20 people in each room, you know, and they've been dancing, and so they're sweaty and smelly, but they're all crammed right next to one another. Okay, you got the guy that got there early and drank too much of the Dr. Pepper that was in the bathtub. And he's throwing up in the toilet, you know, you got the couple in the corner making out, and they say, hey, let's get a room, and you say, oh, wait, they did. You know, but you're there, hey, this is prom, this is fun, I've been waiting, I'm a junior, I'm a senior, this is, but you're really not having fun.
Yeah, there's no social distancing there.
Well, that puts a whole new spin on everything, but, so you're there, and you're not really happy there, but you don't want to, this is prom, I'm just being weird, I'm supposed to be happy. But then you find out that, hey, somebody says, hey, this isn't cool, I'm not here, I'm not having any fun. Oh, you're not having any fun? I'm not having any fun either. So when one leaves, all the rest kind of follow along with them, okay? And then all you're left with is the guy that's passed out in the bathroom, you know, and then maybe the guy that's taking care of that guy that's passed out in the bathroom, and then the couple that's still making out in the corner. And so they're back to 4, which is what the room is designed for, okay? So what I've made right here is a supersaturated solution. Just act like you don't see anything down here at the bottom, okay? Because it's not supposed to be there. But if I take one more, this is sodium acetate. If I take one more grain, one person, put it into it, now, hey, if you're not happy, I'm not happy. If you're leaving, I'm leaving. And so one by one, little by little, all of the extra solid that's dissolved in there ends up crystallizing and precipitating out, and we end up now back to where we have what's called a saturated solution. That's pretty cool, wasn't it? Now, field of testing. You saw that I took it out of the ice bath? Go ahead and just pass it back. Okay?
It's like cold at the top.
Well, it's cold because I had it in the ice bath. It's
Yeah.
only hot where the reaction took place. Okay, now, what this is sodium acetate monohydrate. Okay? So it's a hydrate as a solid. All I do is take the solid and heat it and put it into boiling water. The boiling water causes the water molecules to break apart from the ion, that hydrate. I don't add any water to it at all. So I just take this, I use it year after year after year. I just take this and put it into hot water. And that separates the water from the ion. Okay, again, sodium acetate monohydrate. So there's water trapped in here. But it's so soluble in the water that it'll dissolve in that water of hydration. So I don't have to add any more water to it. I just get it to where, so I'm making a saturated solution at a high temperature. Then I cool it down, put it in the ice and get it cold. And so now it's super saturated. So I put 1 seed crystal of sodium acetate in, and that caused all the extra amount to come out. Okay? Now you don't just make a supersaturated, they're hard to make, and again, only a few substances do it. So in Chemistry 1, some of the teachers actually taught that you make supersaturated just by adding more stuff. And that's not true. Okay? If you add more stuff, it's just going to go to the bottom most of the time. To make it supersaturated, you heat it up, make it saturated, then cool it down slowly. Now, so I took this, it was boiling water, but then I put it in the ice bath. Okay, so I had to add heat to it to make it dissolve. It was an endothermic process. In order to make it dissolve, I had to put a positive heat of solution. So I put energy into it. Now the surroundings, everything got hot because of the energy I was putting into it. But then when I put it in the ice bath, those molecules that separated, okay, that they went into solution, we forced them into solution. Now they're gonna come back out of solution, okay? When the bonds begin to form back and make the ions go back together, they're gonna release energy. That's why it got hot. I took it out of the ice bath, it's cold, but the heat, when those bonds and the ions came back together and formed a solid, released the energy, the same amount that I had to put in to make it dissolve in the first place. So energy is reversible. So that's what a supersaturated solution is. So we have unsaturated, saturated, supersaturated. All right, last thing, effect of pressure. Is this in the field of view here?
Yeah.
Effect of pressure on solubility. And this one's easy. For solids and liquids, oops, no effect. Okay? So if you put pressure onto any kind of sugar in water, salt in water, it's not going to have any effect on how much dissolves or not. Molecules are already pretty much right as close together as possible. It's not going to have any effect. The only thing it's going to affect is gases. Okay? And they follow Henry's law, which simply says solubility of a gas is directly proportional to the pressure on the gas above the liquid. All you gotta do is think of a 2-liter bottle of Coke or any soda. So a 2-liter bottle of pop, if we want to be, generic. When you buy that at the store, it's firm, right? Why is the bottle firm? The pressure of the CO2 gas, and it's really the pressure of the CO2 gas in that little space above the liquid. Okay, that pressure is causing keeps the water from being, if you were to squeeze it, the water would try to go up into that little space, but the pressure of the CO2 is keeping that, so everything's firm. Okay? So as soon as you open that up, which is why they call it pop, psst, you hear that. What do you begin to observe?